Well, it's a pleasure. I think this is Dave's third time back here as a speaker.
Not enough.
Yeah, not enough. We try and get him back every year, and I'm so glad that we can get him again this year. Dave is the director of the Henry B. duPont III Planetarium at the Discovery Museum in Bridgeport, Connecticut. He's talked about all sorts of stuff. He's very active with the high altitude balloons that he's working on with Mike Mazakevich. They're doing, Dave has talked about the CubeSats that they've done. There's a lot of different things that are going on at the Discovery Museum. We have a really close relationship with the Discovery Museum, and we like to do anything we can with them, and we're so glad that Dave reciprocates with us too. So please welcome back Dave Mestre.
It's really great to be here again at the Rolnick Observatory with you guys at Westport Astronomical Society. I just wanted to kind of, by way of introducing this talk, when we think of astronomy, especially among the club members here, I'm sure you probably think about it as the modern hobby that it is today, with all of the instruments that you use and modern telescopes. This hobby has come a long way, and you're practically doing, at least with the instrumentation that you have today, what would have been considered back in the 50s and 60s modern astronomical research, which is pretty remarkable. But one of the things that I want you to leave this talk with is the idea that that people have been looking at the sky with this yearning to understand the underlying mechanisms by which the universe works. And what's amazing about the machine that I'm going to talk about is that heritage of looking at the universe and trying to understand this underlying mechanism behind it is incredibly ancient, and probably inspired one of the most unbelievable instruments, one of the most unbelievable machines to come from antiquity that has caught people completely by surprise with its complexity. And I hope by the end of the talk you'll appreciate the complexity of this machine. So let me talk a little bit about this machine and where it was discovered. The machine is known as the Antikythera Mechanism. And so we will go back to a time around the turn of the 19th into the 20th century. It was the spring of 1900. And the story goes is that there were some sponge divers from the island of Simi. A storm brought them to shelter around an island known as the island of Antikythera. Once the storm had cleared, the captain decided that this would be practically a good place to attempt to do a little bit of sponge diving. Now, to do the sponge diving, you needed to wear very heavy equipment, diving helmets, and they sent one diver down. And when this diver went down, he immediately wanted to come back up again, because what he saw, the way he described it, is he saw the floor was littered with bodies. And what he didn't realize was that he was not looking at bodies, per se. What he was looking at was probably one of the greatest treasure troves of Greek artifacts that had ever been discovered. What he had seen were statues, bronze statues, some marble, but it was clear that this was an archaeological site, the likes of which had not been seen before. The report is made in November of 1900, and real earnest diving operations begin 1900 and into 1901. I'll show you a couple of pictures of some of the sailors here. So you can see the style of diving equipment that was used at the turn of the century to do the kinds of sponge diving that these sailors did. These are members of the crew that were on hand to actually start to retrieve these artifacts. The Greek government actually hired the sponge divers to be part of the diving crew to actually go underwater to retrieve many of these artifacts. Just to give you an idea of how tough these guys look, here's the captain of the ship right there. I would really not want to be on his bad side. These are just kind of the kind of hard life that these Greek sponge divers kind of live.
Woman to it.
Yeah.
And that lady, scary.
Yeah, she's even, I would not want to be her.
Look at the kids.
Yeah, I know, the kids are really, seriously.
Kids aren't happy.
Yeah, I know. It's a rough life. This is a really rough sponge diving life.
Where is the Simi Island?
That's off the. I think it's off the coast of Greece in the Adriatic. I think it's oh gosh, the danger area. I've got a map of where the site is located.
Okay.
So I'll show you what we think was the route of the ship. That is the source of the ship, the artifacts of the shipwreck. This famous diver by the name of Jacques Cousteau gets intrigued by this project, and in 1953 he starts diving in the Antikythera area, and he's sponsored by National Geographic. He's so drawn to this site that he actually pitches an idea where he wants to actually create a series of underwater documentaries. And in the 1970s, I don't know if you're familiar, I actually remember this series. Where Jacques Cousteau actually created a series called the Cousteau Odyssey. And this one episode, known Diving for Roman Plunder, where he actually went underwater to the Antikythera site and actually started retrieving artifacts from the site. The big artifacts were actually picked up around the 1900s, and he starts to pick up smaller artifacts that help us in understanding a little bit more about where the ship might have come from, and a little bit more about the probably dating this shipwreck in particular. But it was actually something that really shocked people in terms of the quality of the kinds of artifacts that were retrieved from this shipwreck. This particular bronze here is only the head that survives. We believe it was actually part of a much larger statue. This is known as the philosopher. Over here, you can see this particular statue right here. It seems to be holding something in his hand that is lost to time. But it may be somewhere probably in the shipwreck site even today. Some people believe that this might be Perseus, and what he's holding in his hand would have been the head of Medusa. So those are some of the ideas that people have. This is here in the Museum of Athens, and they actually have a special gallery just for the artifacts from the Antikythera wreck. And so just to give you an idea of the kinds of incredible artifacts that were retrieved. These are some of the bronze statues. Over here you can see the quality of the marble statues. And as well as some of the simple artifacts that kind of help us in the dating of this shipwreck. We find glassware. We also find some of the everyday objects that probably the sailors had on board this ship. This ship was massive. This ship was very heavily laden with many of these artifacts, and it might not have been just one ship, it might have been multiple ships that were involved in this flotilla that we think was actually the plunder of Roman conquerors as they went around Greek city-states, and they actually began to retrieve and steal a lot of these very high-end artifacts that were probably destined to go to Rome. You can see here that the cargo hold was also laden with these vessels. The style of these vessels help us to kind of date this shipwreck as well. And based on just all of this analysis of recovered artifacts, coins, bronze statuettes, gold jewelry, and ceramic vessels, we have this way of actually bringing all this information together to try and date when this shipwreck actually happened. So based on the amphora, which are the vessels that probably either held olive oil or wine, it indicates probably around anywhere from 80 to 70 BCE. I know that's within about a decade, but roughly around that time. We have pottery that dates from between 75 and 50 BCE. Roman ceramics that are consistent with mid-1st century Roman ceramics. So this is mid-1st century BCE. So within about a century of, that gives us sort of a good date in which this vessel actually probably sank. We have coins that date to around 76 to 67 BCE. And I believe it was Jacques Cousteau that actually picked up many of the coin artifacts while he was actually using a special suction technique. He actually brought down a vacuum that actually would suck up sediment. It was brought up topside, and then it was sieved. And from there, they were able to pick up some of the smaller artifacts. And then, of course, we have in antiquity a record of a shipwreck that was from the time of Sulla, and he mentions shipwreck in this region and a cargo ship or cargo ships that sank around this particular time. Now, the important thing, though, is that these artifacts that we see here are probably much older than the shipwreck itself. So it is possible that this particular shipwreck was actually a plunder mission, where it went around to the different Greek colony city-states. En route, would pick up more and more plunder, probably very specific to the taste of the Roman conqueror that commissioned this expedition, and was looking for very particular artifacts, certain bronzes, certain marbles, very high-end things that were pulled from these particular city-states during this plunder and conquest mission of this type. And so when we think of the route that this thing might have traveled, and this is where I can show you where we think it happened, we believe that it starts around the area of modern Turkey, and it starts going through the colonies. It doesn't go to the Athens or any of these the major city-states. It really goes to sort of the vassal states or colony states, city-states of the Greeks of that time. If you're familiar with history, you'll probably know that Syracuse was actually a Greek colony. It's actually a Corinthian colony, and this Corinthian colony of this Greek city-state of Syracuse and the island of Sicily is conquered by the Romans, and the Romans go around to other Greek city-states and begin conquest and plunder. And most famously, Syracuse is the site of a very famous Greek mathematician and engineer known as Archimedes. Okay? So Archimedes is famous for not it was drawing all sorts of stuff in the sand, and a Roman soldier kills him because he didn't listen to the Roman soldier. He was so fixated on what he was working on. And so this is around sort of the time of probably about a century after Archimedes, and around the time when you start to see Roman dominance in this region, and city-states starting to fall to Roman conquest, and these are the fruits of the plunder of these Roman expeditions. Then there's this thing. So when it was first discovered, it was picked up off the ocean floor, or it was picked off the seafloor, and it was kind of cataloged, but nobody really knew what to do with it. It was an artifact unlike any of the artifacts that captured the attention of many of the archaeologists of the time. So when compared to the bronzes and the marbles, the glassware, the riches of the Antikythera wreck site, this practically gets no attention whatsoever. In fact, because it has such a modern look to it, it's a gear-type mechanism of some sort, it is first assumed that what they're seeing here is something that actually fell onto the same site as the wreck, but was probably something from the 19th or something from the, clearly maybe something that's a lot more modern than any of the other ancient artifacts. And there it stays for a very long time, and is cataloged, and it starts to capture some attention. It turns out in the 1920s and 1930s, a Greek admiral of the Navy discovers that there is this artifact that exists in the collections that was picked up from the Antikythera wreck site. And when he looks at it, he tries to decipher the gearing mechanism that is all kind of buried in this really horribly mangled and corroded artifact. But he can tell that there are gears in this mechanism, and there's something that's buried deep inside. And so he thinks that this is actually of the time period or contemporaneous to the shipwreck, if not earlier than that. And nobody really knows what to do with his ideas. It's not until around the 1950s that this particular man really starts to catapult the study of this mechanism, so that people really start to take seriously that this is actually an ancient Greek mechanical device of the likes that had never even been seen before or even imagined that even could exist during this time period. In 1951, he starts to develop an interest in this artifact, and it's not until the 1970s that he's got the technology available to him to actually perform X-rays on this artifact. And based on a few years of studying this artifact under X-rays, does he discover that this is actually a very complicated geared mechanism. And he writes a very famous book called Gears from the Greeks, where he expounds that what you see here is a very early mechanical computer of a type that had never been seen before. And at the time, he doesn't know quite what it's supposed to compute, but he believes it is connected to something astronomical, and leaves it there. And this starts a whole other area of inquiry and interest in the Antikythera device. Now, it turns out that there are other geared devices that we see in antiquity, but not quite this old. We do have an artifact that dates back to the 1200s, of a geared mechanism that happens to be behind an astrolabe. So the front of it is a typical astrolabe. An astrolabe is a device that actually, like a planisphere, can show you what is up in the sky. It tells you the positions of the stars, and it has different disks and rotating faces that can actually tell you where things are in the sky. Very similar to modern plastic planispheres that you see today. What really made this particular device interesting was on the back of it there was actually a mechanism, a geared mechanism. And this geared mechanism actually produced the phases of the moon. Okay, so this is an Arabic device, astrolabe, and geared mechanism that's hidden inside. We do find another geared mechanism that's even older than that. We go back to the 6th century. It's not a complete mechanism, it's just parts of this mechanism. The top corner is actually a reproduction of this mechanism, and this mechanism also does the phases of the moon in that little window. And so as we turn a particular crank or dial, it actually advances the moon's phases in time, and so the phases of the moon appear inside that window. So this is about as old as geared mechanisms get. Notice that though they seem to be complex to our eyes, they really are, I would probably say, one or two trick ponies in terms of gearing. And most of what we see here is really mechanisms designed to actually display the moon's phases, for the most part. What we're going to find, as we start to talk about the Antikythera device, is that device, which is probably 500 to 600 years before this machine, it's way more complicated, much more complicated than we even imagined. If it could do this, we would be impressed. But what we think it's capable of doing is so far advanced that it begs the question: who was the mechanical genius that built this thing? So let's talk about the parts itself. So if we were to take collections of all the pieces that we consider as part of the Antikythera mechanism itself, these are all the parts that you can see right here. You could literally fit them on a 6-foot table, practically. The mechanism itself isn't terribly big. It's probably about this size in terms of the major piece, which is this giant wheel that you see right there. It is clear that some of the mechanism has inscriptions on them. For many, many years, they could not be read with any great facility, so we really didn't know quite exactly what it was saying. And it wasn't until modern techniques were developed that we actually start to really decipher what these words are saying, and then to really understand what the gear mechanisms are supposed to be doing. Best we could do was with X-rays in the early days, and so when you start to see X-ray images, you clearly start to discover that there are hidden inside the corroded pieces. There are other gears in there, many more gears. And at the time when these X-rays were done, it wasn't clear really what these gears were meant to do, other than they existed there. We will discover later on that some of the gears are actually incredibly cleverly designed, and there's one gear that actually is a gear that has a sliding pin mechanism to make one of the dials speed up and slow down. What's that?
Jesus.
Yes, yeah, it's very, very, very impressive. So when we think of this machine, I'll show you a little video right here. There we go. So this is a CT scan of the machine itself. Now what I want to do is I want to kind of take a look at it as we start to really delve deep into this machine and all its different layers. You'll start to see that stacked in there are just layers and layers of very complicated gears. This is not the type that you're going to see in the 600s. This is not the type that you're going to see in the 1200s. This is something so far beyond what these machines of the 600s and 1200s look like. This is completely from a different planet. Literally, just to give you an idea of how complicated this machine was. Yeah, it is a phenomenal machine. So let's take a look at the known gearing systems of this machine and what we think it might have looked like. Now understand that the machine is really in bad shape. And a lot of what we're, or at least I'm sharing with you is really the best conjecture that we've come up with as of about 2012 to 2013, pretty much, as to what we think this mechanism might have looked like or how it actually operated. So this is sort of the easy version, the simple version. And what you will see is that we think that the mechanism itself was actually enclosed in a box of some type. The box has since been lost to time. They had faces, a front face and then a back face. But front face and back face with dials that displayed information. And all was driven with a single hand crank. So all of these dials were all driven by one single crank. So as you advanced in time, the front dial was a calendar and would display the lunar phase, in addition to the position of the moon in the sky relative to the zodiac. And the back, way more complicated. It's a machine that actually can coordinate solar calendars with complicated lunar calendars, would tell you and predict when eclipses would happen, and in addition to which, would also tell you the type of eclipse to expect and at what hour to expect the eclipse. Okay. This is not a machine that we were expecting to see in any form, in any way, from 2,100 to 2,200 years ago. There is no precedent for a machine of this type. This particular machine, if you really want to push the technology, it has been pushed in terms of conjecture. There are hints that the machine might have actually done even more tricks than we originally had conceived. Where the original conception, and the easiest conception, at least we can prove with the gears that we can see, that it actually would display the moon's phases. It would display the anomalistic motion of the moon, its varying speeds as it traveled through the zodiac. But there is some conjecture that it actually would display planetary positions as well. So there's some ideas that it actually had many more dials for all of the visible planets. And at least with the mechanism that we think it was capable of showing things like where you would expect to see Mercury and Mars, and Jupiter and Saturn. So it's a pretty amazing machine to consider. We also think that the machine probably had a door or maybe some kind of covering. We've noticed that there are what appear to be a face of some type where we found bits and pieces that tell us that this machine actually had instructions on how to use it. In addition to which, there is on the front face, where the front face dial is, where we know that there's a lunar dial and a calendar dial. There's a ring around the dials that showed two things. One ring was for the Egyptian calendar, with the months in the Egyptian months calendar. There's a secondary ring, which is a ring for the zodiac. So it is also corresponding not only calendar events with celestial events. But what's really interesting about the Egyptian calendar was that the dial itself could actually turn so that you could add a leap day when you needed to. So you can actually adjust the calendar so that you could correspond to the actual timekeeping that was in use at that time. In addition to which, you will see that there are actually markings along the calendars, and they're Greek symbols. And what they do is they're Greek symbols that actually correspond to inscriptions at the bottom, much like look at A, and it would correspond to A down here, and A meant this is the helical rising of a particular cluster of stars, as it would be seen during this particular time of the year. We think that these were inscriptions that were added afterwards so that they could make the machine more and more accurate in terms of being able to show you when celestial events could be expected to be seen in the sky. We have back here the back plate. The back plate is corresponds to the eclipse calendar, which can predict eclipses. And then we also have a calendar device that actually was used to correspond the cycles of the moon and the moon's months with the solar calendars of the Egyptians. So it's an incredibly complicated device. Just to give you an idea, someone back there was good with ancient Greek here. So this is one of the pieces, and just to give you an idea of this was not possible during the time of the Sola to be able to decipher. This is actually a special technique that was used to actually pull out these inscriptions. And the way that I've seen it, it was actually in the documentary. They would take the artifact and they would put a globe on top of it, and this globe was literally covered with cameras. So you get all sorts of views of this object, and they would flash all these little flashes at different angles. And based on the shadowing effects, you could actually start to pull out inscriptions. And that was not done before. That was pretty remarkable. And with this, it revolutionized the study of this, because for the first time now we could actually start to read the inscriptions that were on all of the different faces, at least the remnants of those faces. And that's where we pick up things like the months of the calendars that were used during that time. In addition to which, we get it down to the point where the names of the months are incredibly specific to a calendar that was only used by those that were from Corinth or from Corinthian colonies. So for example, there's the month name called Phoenicius. Nobody uses that name in one of their calendars. That is a specific name that's only used by certain Corinthian colonies, of which Syracuse is one of them. Okay, so that's very, very intriguing. Let's take a look at probably one of the, this is not a one-trick pony kind of a machine. There are lots of tricks that this thing can do, and one of the most incredible is, of course, its ability to predict eclipses. And this is the thing that's really, really kind of remarkable about this machine. So let's take a look at the dials as we can decipher them. So this would be considered the back of the machine, okay? And the way that this machine works is that there's a shaft that comes out here and an indicator that basically runs around. This is actually a very carefully crafted basically groove of some type. It's actually just it's kind of like an opening. And what you did was that the dial had a little needle or a little panel, a piece of metal that actually slipped into this groove. And as you turned your mechanism, the dial would turn and it would actually slide along this giant spiral, and the indicator would tell you which one of these little panels you needed to read. This side, of course, is the eclipses. So this was an eclipse predictor. Now you're going to notice that there are all sorts of different inscriptions. What's amazing about them is that these inscriptions said some really interesting things. It would say whether or not this was a solar eclipse. It would tell you whether or not it was a lunar eclipse. In addition to which, there were pieces of information that could tell you what type of lunar eclipse you were expected to see when in the future. For example, there are some that tell you that the eclipse is going to be red. So if you're familiar with the eclipse that happened last time, the lunar eclipse sort of had that little reddish tinge. It knew that it was going to be a reddish tinge, so those kinds of things. It would eclipse solar eclipses, so forth. In addition to which, though, the way that it used this particular cycle, it knew that typical eclipses were separated by a certain number of months or lunar months. that cycle known as the Saros cycle of lunar months would tell you that from one of these eclipses to the next eclipse after one Saros cycle, which is about 220 some odd months, lunar months, you would expect to see your next lunar eclipse. The thing though is that these eclipses would occur at a different time. And so this little dial right here would tell you that if you observed an eclipse here, and it's predicting an eclipse, the dial would come back to this point after one Saros cycle, but the dial here would move. It's telling you at 8 hours, because the eclipse that you saw here, when it comes back one Saros cycle later, is going to be 8 hours from the time you saw it first. And then it'll go around one more time, and then to the next Saros cycle, and when the dial was in the third little quadrant here, it's telling you add 16 hours, because that's when you will see the eclipse that next time. So it was able to predict practically down to roughly the hour when you would be able to see these eclipses. Okay? And these were based on observations collected and then annotated onto this device so that it could actually be used to predict eclipses into the future. Over here, this is actually a lunar solar calendar device. And what happens is that it used a cycle known as a metonic cycle. And one of the big problems with calendars was that, that there were different systems that were used to mark the passage of time. Now, some people use a lunar calendar, which is the phases of the moon, to help us mark the passage of time. And others used a solar calendar, which was careful observations of the sun that would help mark the passage of time. The problem was that the two calendar systems weren't easily divisible into each other. We think of there are 12 months in a year, but it turns out that there aren't exactly 12 lunations, which is one full moon to the next full moon. That's why you may have 12 full moons in your year, or maybe even 13 full moons in your year. And so what this system did was help you to determine, based on what lunar month and what solar month, using the Egyptian calendar, it actually corresponds those two systems. So you can actually get real accurate correspondence between two very different calendar systems, one that uses the moon and the other that uses observations of the sun. And why would you want to do that? So that you can make sure that your predictive power for these kinds of very powerful events was really, really accurate, no matter what calendar system you used. It was pretty remarkable. Over here, this dial that you can see, this actually was a 4-year dial. And this 4-year dial actually marked all of the major Olympics that would happen in antiquity. So it actually would tell you that if this is the calendar year for this Olympic, these are the events that you would expect to see, and these are the solar or lunar eclipses that you would expect to see from then on into the future. Pretty amazing machine. So there are about 38 lunar and 27 solar eclipses that are at least predictable by this machine. There are actually special symbols that tell you the type of eclipse, and also would tell you whether it's a glyph for the moon, glyph for the sun. These glyphs told you whether you were going to be expecting a lunar eclipse or a solar eclipse. And then there were these special symbols of the day or of the night, or hour of the night or hour of the day. These would actually tell you when you would expect this eclipse to occur, particularly kind of like roughly the time. Okay. Now, of course, though, if you got this spacing of eclipses, maybe you can go to a planetarium program and figure out, okay, well, what time period could you match all of these different eclipses and solar eclipses? And it turns out that it's a little hard to do that because there are almost about almost 121 possible start dates for the time that this could predict eclipses into the future. Roughly. It's not exact, but it's a rough estimate. But what's really interesting is that I recently read a paper where they did a little statistical analysis, and what happens is that this machine predicts these eclipses the best if you start it somewhere around 200 BC. Which is interesting because that means that maybe the machine is much older than the shipwreck itself. So, as I mentioned to you before, here's a dial that predicts what we're called the Pan-Hellenic Games or the Olympic Games. And what you see right here along the outside of this dial are the cities in which these Pan-Hellenic Games would occur. And so this was actually able to correspond the Pan-Hellenic Games cycle of every 4 years with the broader calendars or calendar cycles that the Antikythera Mechanism was capable of using as its timekeeping mechanism to be able to predict when the eclipses would occur, to predict when to expect your Olympic Games. Now this is probably the best trick, one of the things that this thing can do, which is really remarkable, is that the moon dial has a mechanism that allows it to change its speed and tells you where to expect the moon to be in its position in the sky as it moves along the zodiac. And so there is this hint that the moon dial had a special gearing mechanism that allowed it to spin a rotating ball to correspond to the phases of the moon. That's really spectacular. There aren't the gearing mechanisms that I showed you that go forward in time to the 1200s and 600s, they don't have this level of complexity at all. Then, what's really amazing is this little gear that's right here. So what happens is that there's a mechanism that when you turn that crank, it will turn these dials. The yellow dial, which is all underneath the blue dial, has a pin that sticks up. And that yellow gear is actually off center of the blue gear. The blue gear is driving the dial for the moon's position. But the yellow gear being offset and sliding this pin up and down this slot, the combination of this pin and slot and off-centered gearing mechanism makes the blue gear speed up and slow down. That's incredibly impressive to do that. And that was something that was only recently discovered, probably within the last maybe 10 years or something like that. But improvements within the last decade. The idea that you actually have this sliding pin mechanism to actually make that anomaly. It's very spectacular. So when we think of the gearing mechanism, this is sort of a side view so you can see how complicated this machine really was. So when you contrast this to the machines that we will see in the future, in the 600s during the time of the Byzantine Empire, to the 1200s, in an astrolabe that belongs to some Arabic nobleman, possibly, that had this very sophisticated machine, there is no comparison between these two machines. There's no comparison to the machine that is the Antikythera Mechanism, which, by the way, we have probably a very good understanding of the back of the mechanism, but we really don't know very much about the front of the mechanism because that part has been lost. So we don't have any other dials of the front. We don't have a lot of the front to really kind of give us an idea as to how that mechanism actually worked. The dials themselves have been lost to antiquity. So when we think of this mechanism, you know, the simplest ideas that we have are that the mechanism had a moon dial, a calendar dial, a dial to show you the position of the sun in that calendar, an Egyptian calendar, and a zodiac. So it was practically not only a timekeeping mechanism of some type with predictive power, but it was also, in sort of a weird way, kind of like a planetarium. A primitive planetarium, at least when you compare it to the planetariums of today. But maybe planetarium primitive is probably not the best word to describe this particular kind of a machine, because this is incredibly complicated. Now, if you really want to push it, you can really go and add way more gears And in 2012, there was a paper by Freeth and Jones where they speculated that there were more things that the machine could do, because as they read up on old texts, there were hints that there were machines of this type that actually performed these kinds of predictive functions. They were translated, or the word was translated as orrery of some type. But nobody in that time, when they translated that word, had the conception that what they were referring to might actually have been a real machine. That's the thing that's pretty remarkable. Now, Freeth and Jones, their idea is that the machine probably could do more things, so they add a couple of extra dials. Some of these dials are things that show you the positions of the planets, and so this is sort of like one of the real stretch in terms of conjecture of what this machine could actually have done and the way that these gears could work. So we're going to see a montage here. This is sort of the mechanism as it's seen. We're going to have this big drive wheel. This drive wheel, one rotation of which will correspond to a year. And it's all driven by this input wheel. And that input wheel is the wheel that's on the outside that when you turn it, drives the entire mechanism. So for the calendar train, you can see the complexity of the mechanisms that are involved in just to drive the rest of the calendar systems. We also have the lunar gear train here. You're going to see that's the slipping mechanism right here, the slot that slides back and forth, or the pin that slides back and forth. And all the different cycles. We've got the cycle of the number of lunar months that correspond to about 19 years. Not exactly the same, but we have some. But just to give you an idea of how complicated this machine here. So this is the prediction of the eclipses. And then when we go to the front of the machine, where it gets a little bit more conjectural, that's when we start to add the idea that maybe it could have done other things, like to predict the positions of planets. And so, at least in this conception, this is what they perceive would be the best kind of gearing mechanism with the technology that they had at the time to be able to predict the positions of the planets. Now, of course, if you're familiar with the planetary motions, you know that all bets are off when it comes to Mars, because Mars' orbit is so eccentric. So even though it had made, there's conjecture that it might have had a Mars wheel, and that Mars wheel probably would never have been incredibly accurate, because you would have to have understood gravity and knew about elliptical orbits in order for you to really predict the motion of Mars. But what's really amazing is that the Greeks had this concept that the universe and the way the universe worked was literally like this, like a machine, like a geared mechanism. And so to build a machine that could do this was to literally build a box in your hand that was the universe and the way the universe worked. This is a pretty profound thing to say, in that understanding how this machine was built gives us an insight into the way these ancient Greek builders were thinking when they were literally unlocking the secrets of the universe and capturing it in a mechanism of this type. That's the thing that I find incredibly remarkable. Which really begs the question, who could build a machine like this? And we know that the Romans never built a machine like this. They stole a machine like this. They didn't build it. So we see in old records that there is mention of these things that are called orreries. They're something that was able to have some kind of predictive power, that was able to show the positions possibly of the planets and the moon. So there are stories of these machines even dating back to around 135 BCE, 51 BCE. This is Poseidonus of Rhodes, and he is credited with being one of these people that actually sort of built a machine of this type. So we're seeing already that this is sort of near the time period in which this machine might have been found. And then we go back a little bit further, and this is Hipparchus, and Hipparchus's contribution is to actually come up with the underlying mathematics in order for a builder to replicate the motion of the moon and the cycles of the moon and all that. So this is where, you know, we need a very clever mathematician who's taken observations from ancient cultures that are more ancient than the ancient Greeks, which is very remarkable to say, and encompass all that information, collect it, aggregate it, and come up with mathematical models in order for people to predict things like eclipses and the calendarization of time, basically. But then, of course, we got this guy right here. Aha, Archimedes. Now, why is this guy important? And this guy is important because this guy was the original gearhead right here. Okay, this guy. And I mean gearhead really with that term because he has been actually documented to have actually built geared mechanisms. In addition to building some pretty remarkable weaponry as well to defend the city of Syracuse from Roman incursions. He was noted because he actually built a geared mechanism for the Romans themselves. And that geared mechanism was actually an odometer. And the story is that he actually built this geared mechanism with a differential gear because this cart had to make turns. And if you make a turn, the inner wheel will have to travel slower than the outer wheel, which is pretty remarkable to do. And we believe Archimedes was able to master this special differential gear. And then he had a special system to actually drop marbles into a trough, and every marble was a distance unit that would help the Romans to basically map out the lengths of all of their highways. And that was the contribution that Archimedes made to the Roman road system to allow the Romans to know the distances of their roads, and built this odometer for them. Now, am I speculating that the machine was actually built by Archimedes? Maybe not. It is tempting, primarily because the cycles of eclipses could fall into the band of time in which Archimedes was alive. We also know that Archimedes built geared mechanisms of a type that are much simpler than the Antikythera mechanism. Now, there is speculation that this machine probably was not built in Syracuse, might have been built in Pergamon or someplace else. And the reason why is because that those were places where the school of Archimedes migrated to. And it is possible that the engineering of Archimedes survived in other colonies to be incorporated and advanced to a stage where it was even possible to build the Antikythera mechanism. But after that time period, gearing mechanisms of this type no longer appear in antiquity. We don't see anything like this ever again until the 600s and until the 1200s, with these very simple artifacts that start to come out of history that tell us that people were using these geared mechanisms. But even then, they're not of the complexity of the Antikythera mechanism. Now, it actually turns out that this year, it was 2015, end of 2014 into 2015, there was actually an expedition that returned to Antikythera. And the reason why they came back to Antikythera was with the hope that they could find more pieces of the mechanism to help us understand a little bit more about its function and its builders. Since then, the artifacts that have come up are bronzes and other statuary, but as to this date, there is no indication that there's anything that even looks like a mechanism that could be added to the Antikythera. The hope is that if this Roman general who went on a little shopping spree in the Greek colonies, if he saw one of these mechanisms, I guarantee you he would have wanted not one of them, he would have wanted all of them if he had seen them. So it is possible that there might have been more, but we don't know. We simply don't know. But every once in a while, people are inspired by the Antikythera mechanism, and I don't know if you've seen this in this video, which is really kind of cool, and I'll show it to you right now. parts it needs just to do the Antikythera and just to do the eclipses of the Antikythera mechanism.
Those guys work for Legos?
They must be master builders with Lego to build a machine like that. But it's I mean, it's like 1,500 parts just to build the part of the Antikythera mechanism that just predicts eclipses. So I can imagine what it would be to actually do a fully functional.
They had to spend a year doing it.
In months, yeah, they did months, but it probably even longer just to actually conceptualize how to actually do it. Because the Legos, they're all standard. So
They're all standard?
Yeah, you can't get like a 223 tooth gear. You'd have to actually print that out and then use Lego, whatever is the construct for Lego, to actually put it into play. But those are all standard. You can buy, if you get 1,500 of those parts, you can build that machine. Yeah. Yeah, it's pretty wild. Yeah. So I mean, I think it leaves everybody kind of scratching their head as to exactly who could have built a machine of this complexity. Are there other machines of this type that are lost to antiquity or waiting to be found? And I think it kind of leaves me with sort of the great line that comes from My Big Fat Greek Wedding, where one of the guys says, the Greek father says that you guys were swinging from trees while we were inventing philosophy.
That's true.
This is true.
We're still swinging that tree. That's a problem.
Yeah, sure. So thank you. Help,
Well, I have a few things. One occurs to me. You mentioned 19. You mentioned something about how many times something for 19.
Yeah, so there's a cycle. It's called the Metonic cycle, and it's 19. You can evenly divide 19 years into, I think, and Tom, correct me if I'm wrong, it was like 223 or 235 lunar months. There's a number there, and it's fairly accurate, but it isn't terribly accurate. So if you stretch the cycle out from a Metonic cycle to this cycle that's about, I think, like 76 years, then the number of months that you can fit into that longer cycle is off by about a day.
Well,
so that's why the calendar can do that.
It makes me think of the precession of the equinoxes.
Yeah.
But I was going to also say is the lunar nodes.
Mm-hmm.
They come back to the same position every 19 years.
Yeah.
And so to get the lunar nodes, you have the cross, of the moon and the sun.
Yep.
So that struck me as maybe there's something in there with having to do with the lunar nodes.
Yeah, I mean,
the 19.
it's just
It's what they use for times.
Yeah, it's over time. You start to correct out those precessional effects. So there are precessional effects that are due to the precession of the Earth, and then there are precessional effects that are due to the precession of the actual orbit of the moon itself. And so things like the phases of the moon, if you use that sort of as your unit of time, putting the moon back in the same position in the sky, getting the exact same lunar eclipse, you have to add these extra corrections to it.
Right.
But you would have to have many observations of the moon in order for you to know that these precessional effects are actually there. But they were known. In fact, the precessional effects of the Earth were known because they knew that all the positions of the stars were changing.
Right.
And then the where the vernal equinox would occur in the sky, that was changing as well.
Yeah, actually, it struck me that that outer split ring that you were talking about could possibly be used as a precessional indicator as well.
Yeah, because it's in aggregate over a very long period of time, the precessional effects probably become more and more reduced as you have more and more lunar months to kind of correct out for those precessional effects. Yeah.
Is the moon phase locked to the sun anyway, or is this all coincidence?
No. It isn't. The problem is that when you're the time period of these lunar events, the lunar months, they're not tied in any way to the solar calendar. So the problem was that there were different calendar systems, one that used lunar calendars and one that used solar calendars. And so what this was a way to translate between those two systems, because some communities would use a lunar calendar and lunar months, and they would just basically add the lunar months, and you would just basically have a cycle of lunar months, and they would come out of phase with the solar calendars of the Egyptians. So there had to be a way to kind of say, an event that happens in the Egyptian calendar corresponds to this month of this particular lunar year. So the Jewish calendar is like that. It adds a whole lunar leap month in order to correct for the out of phase of the solar calendar with the lunar calendar.
Yeah, was the device built based on just purely observational data, or did the Greeks have some conceptual understanding of celestial dynamics at the time?
I want
Is
to
there any theory involved?
Their level of celestial dynamics was based on the observations of more ancient cultures, where they found that there were cycles. The important thing was, I think, is that having the understanding that events in the sky are cyclical now affords you the opportunity to be able to have some kind of mechanism or mathematical model to be able to predict these events. So for example, the eclipse events, they happen over a series of lunar months, something like 200, I want to say 35, a number escapes me, but there's a certain number of lunar months that will take you from one lunar eclipse back to the same type of lunar eclipse, but it may be 8 hours off. And so if you add more of these cycles from one eclipse to the next, eventually 3 turns of the Saros cycle will get you back to a type of eclipse that you saw originally, 3 cycles ago.
So their concept of the solar system and the structure, they didn't really have a good understanding of that.
Yeah, so the idea of this is, so one, you have a purely geocentric model of the universe. And then the idea that they have these sort of nested crystalline spheres. And the mechanism that drives these crystalline spheres is something that they think is based on maybe a gearing mechanism, but definitely is based on things like circles. That's where you have epicycles and things. Now I think what happens is that the Greeks eventually, when they come to the time of Ptolemy, now this turns into a purely mathematical model. And so there's a book that comes out, the Arabs will call it the Almagest, or the Greatest. And this is a book that comes from Ptolemy's time. We're talking about Alexandria. And this particular Alexandrian astronomer creates a model that has incredible predictive power, not only for the moon in the calendar, or the calendarization of these different events, but of the planetary positions too. And that model is so good, it's a purely mathematical model, but that model is so good with the epicycles and all this other stuff, taking wheels of some type, mathematically speaking, and putting them off center and having things turn in this way. If you wanted to, you could literally take that book and build a machine of that type to do that. But that's not what was done. They basically would do this with mathematics, but no one ever built a machine. We don't know whether Ptolemy's thinking of the mechanism that drove all this stuff may have not have been a mathematical thing. It may have been based on something that maybe he had seen or had heard about in terms of a machine that the ancient Greeks had built. maybe a century before, or 2 centuries before, that actually predicted the positions of the planets of the moon.
So that book would have been written 10 BC?
No, I think the Almagest is, so what happens is that we don't know exactly when the book is written, because it's an Arabic translation of what was left behind from scrolls that were just lying around. So what happens is that a lot of knowledge is lost. Alexandria is sort of the pivotal moment where that library gets burnt down and all of those scrolls are lost in there. Some of them are scientific scrolls, some of them are mathematics, some of them are literature, some drama, all this stuff. There's a whole wealth of knowledge that was lost. And what happens is that one of the things that really catches the attention of the Arabs are these texts and treatises on astronomy. And astronomy is incredibly important in terms of timing when certain liturgical events take place, and also when you time prayers, that kind of thing. So that becomes of interest to them. They even have their translations into Arabic where you can actually see that there are things that look like a gear. But the Arabs take this knowledge and they attempt to build machines of that type.
What time frame is that then?
And that's probably around the 12th century, 1200s, the 1100s, that kind of thing. So, and then the 600s, the 500s, 600s, you're talking about the Byzantine time. So there's still vestiges of the Roman Empire, but it's still all a lot of ancient Greek stuff. So that's all kind of lying around. So yeah, so I mean, that it's using these ideas that come from Ptolemy, you're able to create a system of mathematical equations that can predict planetary positions. But maybe it's possible that what Ptolemy was really talking about was that there's actually a machine that does that. And you could build this machine if your gears or your circles do this, and it'll predict the planetary positions. So this is based on Hipparchus, but had this been around during the time of Ptolemy, and you had Archimedes and Ptolemy working together, they probably would have built a machine that was even more accurate. And then what you're talking about is an ancient supercomputer. That's what you're looking at.
But if there's Egyptian on there, then wouldn't you think that it would come from Egypt?
The calendars came from Egypt. So at the time you're trading with all sorts of different kinds of parts of the world. So the Greeks were traders, they were merchants. So different time periods, different calendar systems are in use throughout the ancient world. The only time when a single calendar system is imposed on the Mediterranean is when the Romans come. And then they say, yeah, I know, that's right, we're going to come, and it becomes the Julian calendar. And that becomes one of the systems that will be used.
Gregorian, yeah.
Yeah, the Gregorian comes much later. That's a
Oh,
correction
okay.
to the Julian calendar.
And actually, the Julian was a correction of the Egyptian calendar.
Correct, that's right. Because the Egyptian calendar had 365 and a quarter days. And so, they 365. So they had like 360 days, and there was sort of like a 5-day party. And then the 360 days. So the Julian calendar incorporates the leap year more officially into the calendar. And then what happens with the Gregorian reform is that you just don't need that many leap years and leap days. And so they take away a couple of leap years, and that makes the calendar a little bit more accurate. And the reason why was because they wanted the calendar to align with the seasons. That was the important thing. Because of precessional effects, your calendar will come off season. So that was the big thing. Yeah.
Which Greek historians would have chronicled this, and roughly what percentage of ancient works were lost at Alexandria?
Jesus.
Probably most of them.
99.
Yeah. Alexandria is a huge loss to, at least in the world of antiquity. It's a huge wealth of knowledge that literally just evaporates. What we find is some ancient translations of texts that indicate how many plays were written by famous Greek playwrights. And when you look at the catalogs of plays, you see that there's some of them that are missing that we don't have. You know,
Right.
so based on some catalogs, you can find.
But there would have been historians who would have chronicled this.
There are probably philosophers that we don't even know about that were probably lost during that time period.
Okay.
So in that time period, not only with the fall of Alexandria, with the fall of the Byzantine Empire, the fall of there is an enormous amount of knowledge that's lost. And it doesn't take long. 40 years after the Saturn V launches, we don't have a guy that can build a Saturn V. We have the fine guys that can build a Saturn V. And now we're returning to the capsule style of spacecraft. So now we have to talk to Apollo astronauts how they actually put a capsule together. That kind of thing. That's what happens with knowledge. Yeah.
So there you have it, guys. Let's finish it up.
Thank
Dave Mestre. One of the things I forgot to